Hello Ravens. Today we're going to be looking at an AP Calculus BC free response question from the year 2000. This is question 4 of that series. It's a non-calculator question. What we're looking at is a two-dimensional vector, which is essentially just a parametric function. The question is, a moving particle has position x of t, comma, y of t at time t. The position of the particle at time t equals 1 is 2, 6, and the velocity vector at any time t is greater than 0 is given by 1 minus 1 over t squared, comma, 2 plus 1 over t squared. So unpacking that for a moment, they've given us that the position vector is x of t, y of t, and they've also given us a velocity vector, so not the same thing. This is x prime of t, y of t that they've given us here as this velocity vector. They've given us a domain, t is always going to be greater than 0, and they've given us a particular solution for a position at t equals 1. So what we know from that is it's likely that there's going to be differentiation in this problem because we're looking at vectors, we're looking at position and velocity, and we also know that there's likely to be integration because they've given us a particular solution for the position but a vector for the velocity. And lo and behold, part A and part B are looking for first the acceleration vector at a particular time and then the position vector at that same time. So let's start with part A. Find the acceleration vector at time t equals 3. This is a very straightforward question. They're just looking for that overall acceleration vector and then that particular solution, and that's going to be how the score breakdown ends up. There's 2 points for that. One for the acceleration vector as a function of t, and one for the particular acceleration vector at t equals 3. So we know that we can rewrite this out, this velocity vector they've given us, so that we can look at it a little more easily. This is a t to the negative 2 and 2 plus t to the negative 2 here. So we want to take the derivative of that. We know that with a vector, we're just going to do it individually, end up with our x double prime of t, y double prime t, and here we have a positive 2t to the negative 3 and a negative 2t to the negative 3, just by power rule. It's fairly straightforward. Again, that's 1 point there, and then they're going to ask again for this t equals 3, so we just plug in that value, and you're going to end up with 2 to the 27 and negative 2 to the 27. 1 point, 2 points. Part B is looking at the inverse of that, the position of the particle at time t equals 3. So we just want to integrate that same velocity vector they've given us at the beginning, and we'll take an indefinite integral to start out. And you can count generally if there's a question like that. Of course, you're going to get 1 point for the anti-differentiation. So if we want to take the integral of this, we're going to come out to plus c. You have to remember that you have that here. This is the position function in terms of t. And at that point, this is where we're going to want to go back and look at the t equals 1 and this 2 over 6. So what we can do is we can set this equal. We know that at t equals 1, this whole vector plus the c is going to equal this. And we can subtract this 2, 1 here vector so that we end up with a 0, 5 vector on this side is equal to c. So now we figured out what c is. We can go back and we can look at t plus 1 over t plus a 0, and then your 2t minus 1 over t plus 5. This is your full position function. Essentially what we did there is we knew that the indefinite integral still leaves you with a plus c. We plugged in the particular solution to find what that c is. It's representative of a vector when you're doing integration with vectors. And by putting this in, just adding it, we know that this is the full position vector. Now that's going to get you a second point. This whole question is going to be worth 3 points. 1 for this initial integration, 1 for the use of this t equals 1 particular solution to find c, and then the final one is, of course, finding the vector at s of 3, at t equals 3, which we can just do real quickly to find is 3 plus 1 over 3, which is 10 thirds, and this is going to be 6 minus 1 over 3 plus 5, which adds up to 32 over 3. Now switching back to look at parts C and D here, we see that they're confirming this domain, and part C is asking for what time t is greater than 0 does the line tangent to the path of the particle at x of t, y of t, again they've said that's the position function, have a slope of 8. So we want the slope of the position function, which we can find using our velocity vector, and we want to know when that's equal to 8. What you need to make sure to do here is that since they're asking for the overall slope of the position function and that path, they actually want dy over dx. But what we have right now is a vector that represents dx over dt and dy over dt. So we first want to convert that into our dy dx, because these dt's will cancel out, and so we know that this will end up being our 2 plus 1 over t squared over 1 minus 1 over t squared. You're actually going to get one of the 2 points that are available for this question from just setting this up, this equation. And they'll give you a separate point once you find if you find the solution for t, the actual solution. So we just solve this algebraically. Multiply this denominator over so that we have this here, and this will lead us to finding that t squared is equal to 9 over 6. Essentially distribute out the 8, and then you can add this, you can multiply through by t squared and then move things over. And at that point, it's easy enough to find that t is equal to a plus or minus 3 over 2. But you have to remember, and as they reminded us, that t is always greater than 0 for this, so we have a domain. So you can strike this out, this negative, and know that your actual answer will be just this. It's an important thing to remember you catch that. If you have a domain, which is quite common with both vectors and parametric functions, to go back and check that. So like I said, you get 1 point just for setting this up, which is a great example of how you always just, when you're going through these, always try to set up a function, even if you don't know how to solve it. Set up that equation or that expression that they're asking for, and you can get usually partial credit for that, and you're going to get a 2nd point for this. Now we're going to look at part D. The particle approaches a line as t approaches infinity. Find the slope of this line. Show the work that leads to your conclusion. So what this is referencing and saying that we're getting a linear slope as t approaches infinity, and they want to find that particular slope. We already know from part C that our dy dx is equal to our dy over dt over our dx over dt. And in this case, it's asking us essentially to take a limit. So if we take the limit of this, what we end up finding is that as this goes to infinity, you can plug the infinity straight in. You don't have to do any strange L'Hopital or anything for this one, although they might end up doing that on later questions in the AP exams. This is going to 0, this is going to 0, this term here, so you end up with a 2 over 1, whole thing equals 2. For this question, you're also going to have 2 points. This is a overall fairly simplistic set of problems. All they're asking for here, consider the limit of dy over dx. This here would be 1 point. Those are tied. And then 1 point for this particular answer. However, they do make a note for this one. They say that if there is no consideration of limit, you will get a 0 out of 2 points, even if you get the answer.